and that is optoelectronic devices. So what we are going to learn in this unit is the LDR, that is a light dependent resistor. Then we're going to see the LED, light emitting diode, the phototransistor, an optocoupler, and a photovoltaic cell. So these are the 5 things that we are going to study in this particular unit. We'll start with the basics of light units. So basics of light units. Now there are a lot of units used in physics as far as light is concerned, but we are going to see a few of them which are relevant to us. So the very first thing, the total light energy output. Total light energy output, also called as the luminous flux, which is most of the time denoted by phi s. Okay, from a source can be measured in milliwatts. So this is measured in milliwatts, or also in lumens, LM for short, where, look at the conversion properly, where 1 lumen is equal to 1.496 milliwatt. So you can define the light energy output, rather you can measure the light energy output in the terms of lumens or um, milliwatts. Now many times the LEDs, the lighting LEDs, that is the LEDs that we use for illumination purpose, are measured in terms of watts. Okay, whereas your LCD projector, okay, and even up to some extent the computer screens, they are measured in lumens. Okay. Now the next thing is, guys, am I audible?
Yes, sir.
Okay. So the luminous intensity, the next term is luminous intensity. Okay, which we'll call as ES. Is also called the luminance of a light source. That is, of a light source. It is defined as the luminous flux density. Luminous flux density per unit solid angle. A solid angle is, you can think of it as a cone emitting from the source and it is measured in candelas, CD for short, where 1 CD is equal to 1 lumen per unit solid angle. Of course, this is assuming that there is a point source and that illuminates equally, evenly in all directions. So we have ES, it is the luminous intensity as phi of S. So if you look at the point source, and if I try to measure so light will emanate from all directions. Rather, in all directions. Evenly. And what you have is a cone of light. So this is a cone. Okay. So now this thing is called as flux per unit solid angle. Okay. Now if I want to find out flux per unit area, so what we can do is we can again have the point source and see that the light emitted. If you look at the cross section of this thing, okay, and the distance r. So this is the point source, and we have the flux per unit area at a certain distance r. Okay, this is how you define ES. The light intensity. Guys, am I audible? Guys? Hello?
Yes, sir.
Okay. There was a call drop, I guess. Light intensity. EA. On an area at a given distance from the source is determined from the surface area of a sphere surrounding the source. So it is actually what we are looking at is this. So at a distance of r meters, so at a distance of r meters, the luminous flux is spread over a spherical area of 4 pi r square meters. Okay, you can say that luminous flux is spread over a spherical area of 4 pi r square meters or meter square. So EA becomes phi s divided by 4 pi r square. So when the total flux is expressed in lumens, this particular equation gives the luminous intensity in lumens per square meter. That is lumens per meter square, which is also called as lux. I'll repeat that. So when total flux is represented in lumens, this particular equation gives the luminous intensity in lumens per square meter. So lumens per meter square. This is also called as lux, Lx. So luminous intensity per unit area at any distance r from a point source is determined by dividing the source intensity by r square. So you can just get that these results from the equation. Luminous intensity can also be measured in milliwatt per centimeter square. Okay, I know this is a little bit confusing because there are so many intersecting terms. So luminous intensity can also be measured in milliwatt per centimeter square or lumens per square foot. Okay, which is called as foot candela. Let us not go into those details. Okay, right. Now, once this idea of luminous intensity and lux and all those things are clear, let us go to uh, the actual device, that is the light emitting diode, LED. So one thing we know, this is made up of semiconductor material. So there is a PN junction in this case, and we do have charge carrier recombination. So whenever we talk about the PN junction, there is going to be some kind of recombination, isn't it? What is recombination? What do you understand from recombination of charge carriers? That is, an electron goes and occupies the hole. Okay, let us call it this way. So an electron goes and occupies the hole. This is called as carrier or charge carrier recombination. And this happens in case of the forward bias PN junction. So this is N, this is P. So we have the forward biasing. Like this. And so current starts flowing, that's fine. But at the same time, there will be some recombinations occurring at the junction. Okay. So what happens actually is electrons cross from the N side and recombine with the holes on the P side. Now we know that free electrons have higher energy than holes. Now why is this so? Can anyone tell me? We have already seen PM junctions and we have seen semiconductor physics. Why is that so? Why free electrons have higher energy? Guys, am I
So their
audible?
mobility is more.
No, since they have higher energy, their mobility is more. It's the other way around.
Number of holes equals to number of electrons.
This is energy. All right. We have seen that in the class when there was this online offline mode of teaching, right? So naturally,
Yes, sir.
electron which is there in the conduction band is having a higher energy, correct?
Yes, sir.
Now, where are the holes? Electrons are okay.
Valence band.
Electrons are freely available in the covalent bond when you have the pentavalent impurity and all those things. So you have, let us say this is silicon, this is something else, this is silicon. Say trivalent impurity. What you have the place where there can be an electron. This we call as the hole. But please note that it is, where is it? It is
Attached to.
attached. It is attached in the lattice. It is called as a lattice structure. Whereas if you have a pentavalent atom, pentavalent impurity, in that case, what is the situation?
Already a free electron is there, like
So what we have is
ready to
free electron which
jump.
is available. So that is the reason why this electron is having higher mobility and obviously higher energy and hence higher mobility than the holes. Because holes move in the valence band across from one structure to the other structure. It moves in the, what basically is the movement of, what basically do you mean by the hole moving? होल मूव होता है यानी क्या होता है?
So what you said?
When you say hole, oh, okay, so there is a hole here. That is, there is a place. It's a
Vacancy.
placeholder, right? Now, if it is
Yes, sir.
supposed to move somewhere else, if it is moving somewhere else. Can it float around like this? No. What it can do is this particular hole will leave its place and sit here. In simple plain words, the electron at this location is brought here. So actually, what is moving is electron only. Hole is
Yeah,
not
sir.
moving. The electron is moving, but its placeholder, which we call as hole, it moves in the opposite direction. So as you can see, it moves from one structure to the one, let us say, bond to the other bond. It is not free directly, and that is the reason why it has got lower energy as compared to that of the electrons. समझ में आया?
Yes, sir.
Now these high energy electrons, when they recombine with holes, so if they want to occupy this free electron आ गया यहाँ से, or if it wants to occupy the hole, but hole has got lower energy, na? This has got higher energy. So this electron has to lose some energy. Okay, so the electron has to lose energy in order to recombine with hole. All right. Now this energy, which is lost, it is dissipated in the form of light and heat. Are you able to understand this? this energy is given up in the form of light and heat. Now, if the semiconductor material is transparent or better translucent, this light is emitted and the junction becomes a light source, that is, it becomes an LED. So, this is the basic operating principle of LED. If we draw, let me draw the structure for you so that things will be much easier for you to understand. So you have this kind of structure. This is the junction. Here you have the P type material, and here you have the N type material. So this is P, this is N. This is the anode, and this thing this is the cathode. Okay, and whenever the electrons go from uh, let us say the electrons go from here to here to occupy the holes. By crossing the junction, we see that the light is emitted out of this. All right. So this is how it
Yes, sir.
works. If you look at the construction, this is only the representation in terms of the junction. But if you look at the construction, let me draw it. Okay. So we have this kind of construction. So this is a solid plastic. This is a reflector. This thing is your PN junction. And this block, green one, is the PN junction. This is the anode. This is the cathode. All right.
Yes, sir.
Symbol, all of you know. Is a diode, encircled one, and with this kind of rays coming out of it, arrows coming. So this is the symbol of LED. Please don't forget it. Again, this is the cathode. This is the anode. Okay. But this semiconductor material that is used is not silicon over there. Please remember that. I mean, not only silicon. Okay. So we have different material. So the semiconductor material used is gallium arsenide, GaAs, gallium arsenide, phosphide, GaAsP, and gallium phosphide. GaP. So this gives infrared light. This gives red or yellow, depending on the type of doping. And again, this also gives red or green, depending on the doping. So these are the basic um, materials used in LEDs. Let us have a look at the characteristics and parameters. Now, since it is a diode, what do you expect the characteristics to be? Since it is a PN junction, so LED characteristic curve is similar to what? Semiconductor PN junction diode. Which we have seen quite a lot of times. However, the only difference is that the cut in voltage is not 0.7 volts, but it is 1.6 volts. This is a very important difference. So I can say that the forward voltage drop is 1.6 volts minimum. Please understand this difference. Now reverse breakdown. We have already seen the reverse characteristics. The reverse breakdown is actually very small. In case of silicon PN junction, it was more 50 volts and so on and so forth. But here the reverse breakdown is very less. It is about 3 volts. So you have to take care of while using LED that never let it be reverse biased by voltages more than 3 volts. This is very, very essential. Now the forward current is usually 10 milliamperes to 20 milliamperes. Now this is for the 5 millimeter diameter diode LED that we usually come across. Okay, there are different LEDs with different dimensions and they have smaller forward voltage, forward current capacity. In simple plain words, you should not exceed 20 milliamperes in any case through the LED. And below 10 milliamperes, it may not be visible. Okay, so you have to always make sure that your current is between these two limits, the current flowing through the LED. Now for infrared diodes, infrared LEDs, this forward current can be up to 60, 70 or even 100 milliamperes also. Okay. So typical, let us list down the typical LED specifications. Okay. So you have the luminous intensity, generally it is found at a certain current flowing through it. So you have the minimum, the typical and the maximum. These three columns you will always see in all the data sheets. So the current flowing through the LED is 20 milliamperes and this is 4 millicandela, 8 millicandela. So typically it is 8 millicandela, but it is guaranteed to be not less than 4 millicandela. Then forward voltage, or as VF, it is minimum 1.4 volts, typically 1.6, and can go to as high as 2 volts. Reverse breakdown voltage, that is VR, can be 3 volts or even 10 volts. Please remember, why do we have these three columns here? Minimum, typical and maximum. In one of the assignments, I told you to download the data sheet for a diode, PN junction diode. The reason for that is to make you aware of these things. So why there is this minimum, typical and maximum quoted by the manufacturer? Yes? What is the reason?
So
Why?
for the
See, whenever you have manufacturing process,
so you got disconnected.
that is the reason why manufacturers will always give you the range, that is minimum and maximum, and typical, that is statistically they find out that okay, Most of the times it is, let us say, 1.6 volts. So typical, we call it as typical. Okay. Then we have the peak forward current, that is IF max. So typically it is 90 milliamperes. Peak and average. Average forward current IFAV is 20 milliamperes. But do you see the difference here? There are two parameters talking about the current. One is called as a peak current and as the average current. What is the difference? See, in any situation, this is a very important concept. I can have, so this is time, this is, let us say, the current value. So this LED can take this peak value of current or draw past peak value of current for a very short duration of time, which can be much higher, like 90 milliamperes. But if you want to continuously pass current through it, the maximum limit is 20 milliamperes. Peak can go up to 90 milliamperes, but for a very short duration of time. This is very, very important. This is the basic difference between the peak value and the average forward value. Then you have the power dissipation, PD. Typically it is 100 milliwatt. Then you have something called as the response speed, tau s. So it is 90 nanoseconds. And the peak wavelength, lambda p, in some case it can be like 660 nanometer. Now this is for a specific diode, specific LED. Now depending on the different LEDs, you can have different values over here. Okay. Ideally, this is
Yes.
what you should look out for in the datasheet while selecting the diode LED. Let us have a look at the LED circuits. How to use the LED? So let us say if you have some kind of a device, just like a microcontroller, for example, okay, and you are supposed to connect an LED over there at the output pin, at the output pin. Or okay, let us not, I'll not confuse you with this microcontroller because you don't know anything about that. Okay, so let us say that you want to simply switch on an LED using a switch. So here let us say we have a 5 volts here. Okay. Now since the maximum current, average current is given to us as 20 milliamperes, I cannot directly connect it to the supply. I must use a current limiting resistor and then I'll be using the LED. So this resistance R is very important. Okay, because as soon as I throw this switch on, circuit will get completed and this current will start flowing and the LED will be activated or will glow. It will be visible. So how do you calculate the value of this resistor? Given this value, given a type of LED, so let us say LED here is red. Okay, So how do you calculate the value of required value of R? I'm going
So
to
the
write
LED
down,
will
yes, I'm
off.
going to write down an equation that KVL, the plus 5 volt is equal to the now voltage across the diode is VF. So it will be going to be VF plus I call this as IF into R. All right. So
Yes, sir.
R is going to be 5 minus VF divided by IF. But the problem here is that there are two unknowns. है ना?
Yes, sir.
ये पता नहीं है, ये भी पता नहीं है. तो ठीक है, चलो
Sir,
ये पता है. VF we know that VF is, let us say, 1.6 volts. So 5 minus 1.6 volt divided by IF. लेकिन IF पता नहीं है. तो क्या करना है? How will you solve this? As I said previously, we have to make sure that the LED current is between these limits. I am not going to operate it at the extremity. So I will choose this value. I will assume that value to be, or I will make sure that IF is 10 milliamperes. Now things are easy. 5 minus 1.6 by 10 milliamperes. So now can you find out the value of resistance?
yes, sir.
How much is it? This is what, 3.4 divided by 10 milliamperes. This comes out to be 340 ohms. That is your answer. ठीक है?
Yes, sir.
All right. So that is how you use the LED. Let us now see. Okay. If I want to use, let me see. From this. ठीक है. Okay. Now there are certain different types of LEDs which emit different color. So I'm going to give you the table for the color, the wavelength, in nanometers, the base material, and most importantly the forward voltage drop. By referring to this table, you can calculate the resistance value. Okay, number one is IR, 900 nanometers. Material is GaAs, and for voltage drop is 1.3 volts to 1.6 volts. You've already seen this. To red LED, wavelength is 655 nanometers. GaAsP, 1.5 volts to 1.8 volts. 3 yellow, 5 volts to 2.2 volts. Green, 565 nanometers. GAP, again 2.2 volts to 2.4 volts. Blue 450 nanometer. This is gallium nitride. Drop is 3 volts to 5 volts. Remember this. So it's white. Naturally, it's a mixture of all the blue and yellow. And drop is 3 volt to 5 volts. So this table gives you the information as to what is the base material, what is the wavelength, and what are the voltage drops across that device. All right.
Yes, sir.
Now, I wanted to start with something else, but let me see if we have time for that. I think we can go ahead with that. Okay. So the next material, next device that is what we are going to study is the LDR. It is also called as photoconductive cell. But colloquially it is called as, most popularly it is called as light dependent resistance. What is the mechanism? Light which is striking the surface material will provide sufficient energy to cause electrons within the material to break away from their atoms. So free electrons and holes are created within the material, and therefore its resistance is reduced. Okay. So the basic principle is that light which is striking the surface material will energize the electrons within the material to break away from their atoms. And these electrons and holes which are created within the material, basically when number of electrons increase, what will happen to the resistivity?
It will decrease.
It will decrease. This is actually called as the photoconductive effect. Okay. So if you look at the construction, you slide flat structure here. You have these terminals. This entire thing is a conductor or conducting material. And you have this strip. So this is the terminal. Okay. So this is the conductor. This thing is a strip of photosensitive material. Now, if you look at, it's a resistance essentially, but it is dependent on light. You look at the direction of the arrows. This is the construction. The material. So what material is used? Cadmium sulfide. CDS in short, and cadmium selenide, CDSE. These are the materials used in that photoconductive strip. Now, the response time is comparatively large. I mean, it is a sluggish device. It takes about 10 milliseconds to for CDS and 100 milliseconds for CDSE to react. Change the resistance if the light is incident on it. Spectral response is one very important advantage is that spectral response is similar to human eye, but again it is affected by, this device is affected by temperature. So it is temperature sensitive. If you look at the characteristics, this is resistance in ohms and this is the luminance in lux. So if I mark it 300, 1K, 3K, 10K, 30K and 100K. If I mark this as 1 lux, 3, 10, 30, 300, 100 should be 300 and 1000. Then the response is like this. So what does this tell you? By looking at these characteristics, what does it tell you?
More light, uh, the more the light is, the less the resistivity is.
All right, guys.
Yes, sir. Yes, sir.
Now it is normally specified by what is called as a dark resistance. LDR is specified by the dark resistance. That is when the cell is not at all illuminated, and most of the times it is greater than 100 kilo ohms. So typically it is like 200 kilo ohms when it is dark. And as light intensity increases, the resistance decreases. All right.
Yes, sir.
Okay. Let us quickly see the specifications, typical specifications. You have the power dissipation in milliwatt, maximum voltage, dark resistance, wavelength, sensitivity, and resistance at specified as at 10 lux. So this is normally 200 milliwatts. This is 180 volts. That is AC. Dark resistance is 100 kilo ohms. Wavelength is sensitivity is 550, and resistance as 10 lux is uh, 6 kilo ohms minimum to again 18 kilo ohms maximum. So it may vary like this. Okay.
Yes, sir.
Let us see a typical application to end this session. Very interesting. Can be used in your hobby projects. So we have the LDR here, and we have this value of R.
Sir, you were disconnected in.
So have you gone? Do you know voltage divider equation? You must have started using that somewhere. Voltage divider equation? No? If this is R1, this is R2, this is V, let us say 1, and this is VI, this is VO. How do you calculate VO? VO is given as VI into R2 divided by R1 plus R2.
Plus R2.
This is called as a voltage divider equation. All right. So using that, we can find out the voltage output as V into R divided by R plus RC. Okay. Now to use it, if V is 5 volts, R is 5K, 5 kilo ohms, then at 1 lux, that is 1 lux is dark resistance. What will be the output voltage? VO will be 5 into 5 kilo ohms divided by, assume that the dark resistance is 100 kilo ohms.
100 kilo.
So this is going to be 5K plus 100K. This comes out to be how much? We can calculate it later on. We don't have time for that. Comes out to be 0.23 volts. Now, if the illumination changes from 1 lux to 1000 lux, then from the characteristics we can see that what is the voltage for 1000 lux, what is the resistance. Anyway, there is a slight error here, not exactly like this, but I came to know of it. But okay, something like this. So at 1000 lux, let us say this is the value of the resistance. What is the value? Let us say it is 200 ohms. Okay, for 1000 lux. So calculate the output voltage now after illumination. 5 into 5k divided by 5k plus 200 ohms. How much is that? That comes out to be, which is nearly be equal to 5 volts. To be more precise, it will be 4.8 volts. So do you see how we are able to convert light intensity into voltage values? If you want to measure, if you want to make a lux meter, if you want to measure the light intensity, you can very easily do it. Just break it up like this and measure the voltage. This voltage will give you the measure of light intensity. Clear to all of you?
Yes, sir.
Okay, I think we have already crossed the time limit. So we will stop here for today. Next time we will start with another device, that is the photo transistor, photodiodes and phototransistors. That is. All right.
Sir, actually, the next class has started.
Sorry.
So the next class has started. Can we leave?
Okay. Yeah. Yeah. You can.
Thank you, sir.